Distance learning curricula in machine learning, regression and its applications. Good afternoon and welcome to the machine learning course. This course was developed as a result of the Erasmus Plus project Code-In. All you need to learn is internet access and a computer. The course contains a total of 10 topics, and in this topic, we will say something more about the regression and its applications. Regression is a type of machine learning algorithm that is used to predict a continuous value, like a number. It's like trying to draw a straight line through a set of points on a graph. The goal is to find the line that best fits the data and can be used to make predictions. For example, let's say we want to predict the price of a house based on its size. We could use regression to analyze a set of data on houses and their prices, and then create a model that can predict the price of a new house based on its size. To create a regression model, we need to train it using a set of data known as the training set. The algorithm adjusts the parameters of the model to minimize the difference between the predicted values and the actual values. Overall, regression is a powerful tool in machine learning that can be used to make accurate predictions about real-world phenomena, from house prices to stock market trends. It's generally a good idea to start with simple and widely used algorithms for regression analysis, particularly if you're new to the field of machine learning. Some popular regression algorithms that are relatively simple and easy to implement include linear regression as a basic type of regression analysis that involves fitting a straight line to a set of data points to make predictions. Ridge regression as a variant of linear regression that adds a penalty term to the regression equation to prevent overfitting and improve the generalizability of the model. Lesser regression as another variant of linear regression that can be used for feature selection, as it helps to identify the most important predictors in a dataset and simplifies the regression model. And finally, the polynomial regression as a type of regression analysis that involves fitting a polynomial function to a set of data points, which allows for modeling of more complex relationships between variables. However, polynomial regression can be prone to overfitting, which is a key consideration when using this algorithm. Linear regression is a useful technique for analyzing and predicting the relationship between two variables and can be applied in a wide range of fields, from finance and economics to social sciences and engineering. The goal of linear regression is to find the best linear relationship between x and y, which can be used to predict the value of y for a given value of x. To understand how linear regression works, let's take a look at the scatter plot. In this scatter plot, we have data points that represent the relationship between two variables, x and y. The blue line in the plot represents the best linear fit of the data, also known as the regression line. We can use linear regression to find the equation of this regression line, which is of form y equals beta b0 plus b1 multiply x, where b0 is the intercept and b1 is the slope of the line. We can use this equation to predict the value of y for any given value of x. R squared is the statistical measure that represents how well the linear regression model fits the data. In simpler terms, R squared tells us how much of the variation in the dependent variable y can be explained by the independent variable x in a linear regression model. A high R squared value close to 1 means that the model explains a large proportion of the variation in the dependent variable, while a low R squared value close to 0 means that the model does not explain much of the variation in the dependent variable. For example, if the R squared value is 0.89, this means that 89% of the variation in the dependent variable can be explained by the independent variable in the linear regression model. R-squared is a useful tool for evaluating the performance of a linear regression model and comparing the performance of different models. However, it's important to note that R-squared is just one measure of model performance and should be used in conjunction with other metrics and visualizations to fully evaluate the model. Imagine you and your friend are trying to analyze some data from a survey. You have two sets of numbers, X and Y. You want to understand if there's any relationship between the two sets of numbers. To do that, you'll need to go through some steps. First, you'll calculate the mean of each set of numbers. The mean is just a fancy way of saying average. You add up all the numbers and divide by the total number of numbers in the set. So for X, you add up 1, 2, 3, 4, and 5 and divide by 5. That gives you 3. And for Y, you add up 2, 4, 5, 4, and 5 and divide by 5. That gives you 4. Next, you will calculate the deviation of each value from its respective mean. Deviation is just a fancy word of saying difference. So for each number in X, you'll subtract the mean of X, which is 3. And for each number in Y, you'll subtract the mean of Y, which is 4. This will give you a new set of numbers that tell you how far each value is from its respective mean. For X, the deviations are -2, -1, 0, 1, and 2. For Y, the deviations are -2, 0, 1, 0, and 1. Finally, you'll multiply each deviation in X by its corresponding deviation in Y and add up all those products. This will give you a single number that tells you how the two sets of numbers are related. If the sum of products is positive, that means X and Y tend to go up and down together. If it's negative, that means X tends to go up when Y goes down, and vice versa. And if it's close to 0, that means that there's not much relationship between X and Y. In this case, the sum of product is 6, which is a positive number, indicating that X and Y tend to go up and down together. So, in summary, by calculating the mean, deviation, and sum of products of X and Y, we can gain insight into how these two sets of numbers are related. It's like detective work, where we gather clues and piece them together to solve a mystery. Now that you have calculated the mean and deviation of X and Y and the sum of products of X and Y, it's time to take the next steps to understand the relationship between the two sets of numbers. The fourth step is to calculate the sum of squares of deviations of X. This step involves squaring each deviation in X and then adding up all the squares. This will give you a single number that tells you how much variation there is in X. In this case, the sum of squares of deviations of X is 10. The fifth step is to calculate the slope of the regression line, B1. This is the line that best fits the data and can be used to predict Y values from X values. To calculate the slope, you divide the sum of products of deviations by the sum of squares of deviations of X. In this case, the slope is 0.6, indicating that for every 1 unit increase in X, Y tends to increase by 0.6 units. The sixth step is to calculate the intercept of the regression line, B0. This is the point where the regression line crosses the y-axis. To calculate the intercept, you multiply the slope by the mean of X and subtract the result from the mean of Y. In this case, the intercept is 2.2, indicating that when X is 0, Y is predicted to be 2.2. Finally, you can write the equation of the regression line, which is Y equals B0 plus B1 multiply X. In this case, the equation is Y equals 2.2 plus 0.6 multiply X. The equation tells you that for any given value of X, you can use the equation to predict the corresponding value of Y. So by following these steps, you and your friends were able to analyze the data and understand the relationship between the two sets of numbers. This is a powerful tool that can be used in many different fields to gain insight into complex relationships. Polynomial regression is a form of linear regression that can capture nonlinear relationships between variables by fitting a nonlinear regression line, which may not be possible with simple linear regression 1. It is used when linear regression models may not adequately capture the complexity of the relationship. In polynomial regression, the relationship between the dependent variable and the independent variable is modeled as an nth-degree polynomial function. When the polynomial is of degree 2, it is called a quadratic model. When the degree of a polynomial is 3, it is called a cubic model, and so on. The main difference between the polynomial regression and linear regression is that polynomial regression can model nonlinear relationships between the independent and dependent variables, while linear regression can only model linear relationships. In other words, while linear regression assumes that the relationship between the independent and dependent variables is linear, polynomial regression can model more complex relationships that are nonlinear. Polynomial regression is a powerful tool that can be used to model complex relationships between variables. It is widely used in machine learning and data science to make predictions and to gain insights into complex data sets. We are using polynomial regression to find a mathematical equation that describes the relationship between two variables, x and y. Instead of fitting a straight line, like in simple linear regression, we are fitting a curve to the data. By using the general formula, we can calculate the coefficients beta 0, beta 1, beta 2, etc., that best fit the data. These coefficients represent the slope of the curve at different points and can be used to make predictions about future values of y based on the new values of x. We have a data set with x and y values, and in step 3, we've calculated the sum of x values, y values, x squared values, and x times y values. In step 4, we use these values to calculate the coefficients of the polynomial regression equation using the formulas for beta 1 and beta 0 equals sigma y beta 1 sigma xi n. These coefficients represent the slope and intercept of the curve that best fits the data. And by plugging them into the general formula, we can obtain the polynomial regression equation for this data. The resulting equation is y equals 1.2 plus 0.6x plus epsilon, which we can use to make predictions about future values of y based on new values of x. Imagine you have a bunch of data on COVID-19 positive patients in the hospital over time. You want to build a model to predict how much COVID-19 patients you can expect in the future period. You could use a simple linear regression model, which draws a straight line through the data to make predictions. But what if the data is noisy, meaning there's a lot of random variation in it? The simple linear regression model might end up fitting the noise instead of the true relationship between time and COVID-19 positive patients in hospital. This is called overfitting, and it can lead to bad predictions. Ridge regression helps prevent overfitting by adding a penalty to the model for having too many complicated features. Instead of just fitting a simple line, ridge regression fits a line that's as simple as possible while still being accurate. It does this by minimizing the sum of the squares of the coefficients of the features in the model, while also keeping the coefficients small. Think of it like packing a suitcase. You want to fit as much stuff as possible, but you don't want to overpack and have to pay extra at the airport. So you pack smart, fitting in as much as possible while still keeping it compact. In summary, ridge regression is a way to build a model that predicts something while avoiding overfitting. It does this by adding a penalty to the model for being too complicated. By keeping the model as simple as possible, while still being accurate, ridge regression can make better predictions on new data. Now, let's break down the steps involved in ridge regression. Steps 1 to 4 of ridge regression involve the same calculations as in linear regression. Specifically, in both linear regression and ridge regression, we calculate the mean of x and y, and then calculate the deviation of each value of x and y from their respective means. In ridge regression, we then use these deviations to calculate the sum of products of the deviations of x and y, which is a measure of the direction of the relationship between x and y. The main difference between ridge regression and linear regression lies in step 5. In ridge regression, we add a penalty term to the sum of squares of deviations of x to control overfitting. This penalty term is controlled by the ridge regression parameter lambda, which determines how much we want to penalize the complexity of the model. The value of lambda in ridge regression is a hyperparameter that needs to be chosen by the user based on their specific use case. It is used to control the strength of the regularization term in the ridge regression equation. In this example, we chose a value of lambda equals 0.5 arbitrarily for demonstration purposes. In practice, the optimal value of lambda for a given data set is usually determined through a process called hyperparameter tuning, where different values of lambda are tried out, and the one that yields the best performance on a validation set is chosen. In general, larger values of lambda result in greater shrinkage of the regression coefficients towards 0, which can help prevent overfitting to the training data, but may also result in underfitting. Smaller values of lambda result in less shrinkage and may lead to better performance on the training data, but can also result in overfitting. The optimal value of lambda thus depends on the specific data set and the trade-off between bias and variance. To complete this unit, study and review the following online resources. Thank you for your attention.